Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class. I'm putting it online in case it would be helpful to others as well. There is a link to a printable set of guided notes that you can use along with this video in the description. In this section, we are going to talk all about implicit differentiation, and I just can't wait. I know I say this all the time. I love this section. I mean, I say that for every section, but I truly love this section. Okay, there's something about it that feels good. It's smooth. I think you'll see what I mean as we work through the problems. All right, so the warm-up problems are pretty simple. The first one is, what does the graph of x squared plus y squared equals 25 look like? And usually I let my students struggle through that question if they're not sure. Some of them are pretty confident and know right away. Some not so much. But since we're in the video, I'll just tell you it is a circle, right? This is the equation for a circle that has its center at the origin, and it has a radius of 5. So I'm just going to say, right there is about negative 5, 5, 5, negative 5. And so again, the circle has a center at the origin, and get the right pen. Oh, okay, I can do better than that. I was doing fairly well with my pen skills until that. We're just going to go with it. It's good enough. A circle with a center at 0, 0. And radius of 5. Units. Yay. Next question doesn't seem to have anything to do with the first question, but it does. We'll see. Describe how to find the slope of a tangent line to a curve at a point. Okay, so we know how to do that at this point, right? We know how to do that at this point, right? Let's review. How do you find the slope of a tangent line to a curve at the point? You take the derivative. Find the derivative, whatever you want to say. And step 2, you sub in the point, the x coordinate or whatever is given to you, to derivative to calculate the slope. Okay, my writing is becoming atrocious, but we're just going to go with it. To calculate slope. Now, probably the first time you ever heard the word tangent or the words tangent line was when talking about a circle in geometry, right? I would hope that at some point, when you studied circles in geometry, you talked about a tangent being, a point that, or a line that touches the circle at just one point, like this. Let's make it touch this time. I'm going to have to do it like this. There we go. And so here's what we're going to talk about today. How do you differentiate this equation? How do you differentiate that to be able to calculate the slope of that tangent line? How do you do that? You probably don't know yet, but that's what implicit differentiation is all about. Okay. This equation or this graph is not a function, right? But what it is, it's an implicit equation, and that means that it defines functions inside of it. There's 2 functions that we could graph if we wanted to, say, use the graphing calculator to get this graph of the circle. You would need to solve for y, and in solving for y, you would have the positive root of 25 minus x squared, and you would have the negative root of 25 minus x squared, and those are the 2 functions that you could graph to get the graph of this circle. Okay, that's what implicit differentiation is all about. It is about taking implicit equations and differentiating them, rather than splitting them up into their different functions and differentiating each function separately. Okay, I don't expect that to make a whole lot of sense right now, but it will. It will. Okay, so an implicit equation, I just like to say, is an equation with functions hidden inside of it. Hidden inside. And one of my favorite implicit equations is one that generates this graph, and it's called a folium. Do you have a favorite implicit equation? Okay, I do, and it's this one. So this is just like a general form of a folium. Look at this, though. I can click on this picture and bring up a little bit more information from Wikipedia, good old Wikipedia. And I like to do this because, I don't know, I'm just like a math history buff I've learned over the last few years. And a folium is a famous curve that comes from Descartes. Okay, and I don't know, I just like this story. I remember reading this story, like I read a more detailed description than what is here in the history on Wikipedia, and it just was like so cool to read about. I'm not going to make you listen to the whole story, but I do want to read this little history down here. Okay, the curve was first proposed by Descartes in 1638. Its claim to fame lies in an incident in the development of calculus. There was an incident in the development of calculus. Can you believe that? Like, the development of calculus was not just like this boring thing. There were all sorts of things happening that are just interesting. And here's one. Descartes challenged Fermat to find the tangent line to the curve at an arbitrary point, since Fermat had recently discovered a method for finding tangent lines. Okay, that was like a big deal. Fermat solved the problem easily, something Descartes was unable to do. Man. And then look, you can see what we're studying right here. Since the invention of calculus, the slope of the tangent line can easily be found using implicit differentiation. So cool. So cool. I hope you think it's cool. I think it's cool. All right. So the form of an the equation form, I should say, for a folium goes like this. It is x cubed. Yeah, I am reading this off of my notes. Plus y cubed, because I never trust that I have the signs correct. Minus 3axy equals 0. Okay, that's the form. And notice that there is an a in here. And that A contributes to a slant asymptote that you can see here. Okay, so I love playing around with this equation form, especially in Desmos where you can get all of those different colors. And I like even playing around with coefficients here to try to see what happens with these loops to try to make like a pretty picture. It's kind of fun. I encourage you to do it. Just head over to Desmos Graphing Calculator and, mess around with coefficients to see what you can get out of this. Okay. So an example of this might be something like x cubed plus y cubed minus 9xy equals 0. And in that case, your a value would be 3. Okay, so you could graph that and see what that looks like. You could change the 9 to another number and see what happens. Again, I just think it's pretty cool. So in this section, what we're going to do is we're going to talk about how to take an equation like this one and differentiate it so that we can get the slope of the tangent line equation. Because for sure, as you look at this curve, you could pick many, an infinite amount really, of points along the curve, and you could draw a tangent line to any of those points, and that tangent line would have slope, right? How do you find that slope? You should be able to find that slope. We will. We will use implicit differentiation. All right, so we're not going to start with that equation, though, to show how implicit differentiation works. We're going to start with something much simpler. And the reason I want to start here is because I want to show you 2 different methods for how you can do a lot of these. But I think you're going to find very quickly that you are not going to want to do method 1. Okay, so sorry to waste your time. Skip this part if you feel like you must, but I do want to show you that you could take this equation, y squared equals x. Let's grab a different color. And you could solve the equation for y. Okay, for some of these implicit equations, we can solve for y, and then we could take the derivative the standard way that we're used to doing derivatives. So this one's pretty simple. I square root both sides, right? But what I get out of that is y equals plus root x, plus or minus root x. And so what I really have here are two functions that make this curve. I have y equals the square root of x, and I have y equals the opposite, negative square root of x. And so, I mean, do you have to actually write a derivative twice? No, you could bring along the plus in your differentiation to get your derivative, like this. The derivative of the square root of x, keep in mind that is x to the 1/2 power, right? It is 1/2 x to the negative 1/2 power. Or if we want to write that back in radical form, we could say it is plus or minus 1 over 2 times the square root of x. There we go. Okay, but the thing about that equation form is that, first of all, it took a step of solving for y before we could differentiate. And the other thing about it is that you have to deal with this plus, when calculating your slopes of your tangent lines. And there's really no need for that because we have this thing called implicit differentiation. So let's call method 1 the solving for y method. And let's just not do it anymore. Let's move on to method 2, which is called implicit differentiation. And I think you're going to like this. Okay, implicit differentiation is where you leave the equation in whatever form it is in, and that is, where y is not solved for, and you differentiate both sides of the equation. But here's a key thing to keep in mind. You differentiate with respect to x. Okay, now we could have a big discussion about what that means, what differentiating with respect to x means. It's differentiating with respect to your independent variable. I'm not going to go into too many specifics right now. I'm going to tell you specifically what that means for what you need to do here, just to save some time. Okay, what that means for what you do here is whenever you do a derivative of your y, you then multiply that derivative by dy over dx. Okay, let me show you what it looks like. It sounds scary, it's not. The derivative of y squared is 2y, right? The derivative of x squared is 2x. So the derivative of y squared is 2y. However, if you are differentiating with respect to x, you multiply by dy over dx. The derivative of x on the other side is just 1, as usual. After you differentiate with respect to x, you are then just tasked with solving for dy dx. Okay, and so that would just mean dividing both sides by the 2y, and we easily get our answer. Dy over dx equals 1 over 2y. Woo, it's done. That just looks a little bit simpler, right? The only thing is, it is in terms of y. It uses the variable y instead of x. So if you would use this to calculate slope, you would need to have the y coordinate of the point, where you are calculating. Okay, so let's try another example. Here it is. Here is the folium of Descartes, that I showed you in the opening. I lost my pen. Let me grab that again. Okay, so example 2, you know what? I feel like going with blue this time. Find dy over dx for x cubed minus 9xy plus y cubed equals 0. All right, so this one is a little bit more complicated, and I'm just going to warn you right here for this middle term, we are going to need to use product rule. Keep that in mind so that it's not a surprise when we get there. Okay, so again, what we do here, and this is one where we're not going to solve this for y. Okay, we're definitely not going to use that method 1 solving for y thing. So good thing we said we're not, right? We're going to use implicit differentiation. That means jumping right in with both feet to taking derivatives of everything. You just take a derivative of everything. It's just that when you take a derivative of a y term, you need to multiply by dy over dx. So it looks like this. The derivative of x cubed is 3x squared. Just so you know, when we get back here, let me just talk about this first. The derivative of y cubed is going to be 3y squared times dy over dx. Before we do that, though, what is the derivative of minus 9xy? Okay, so this is a product, and we need to use product rule. I'm going to put a multiplication symbol right here in between the 9x, the negative 9x, and the y to separate into my first function and my second function. And remember, I like to use this little saying for product rule. 1d2 plus 2d1. First times derivative of second plus second times derivative of first. So that looks like this. 1 is negative 9x. d2 is the derivative of y. What is the derivative of y? Well, if I give you something like y equals x squared, the derivative of y is dy over dx, right? Oh my gosh, you use implicit differentiation for everything. The derivative of y is 1, just like the derivative of x is 1, but we put a dy dx there, right? I'm going to lose my pen because I had to erase this, but it was worth it. If anybody watching knows how to set default pen settings in Smart Notebook, reach out to me, please. It's like a struggle, a daily struggle. Okay, so the derivative of y, again, is dy over dx, and what we just wrote right here is 1 d2 plus, don't forget we're not done with product rule, 2d1. 2 is y, d1 is the derivative of negative 9xy, negative 9x, that's our 1, right, negative 9x, and the derivative there is negative 9. I tried to open a parenthesis. Okay, so one more time, that is 1 d2 plus 2 d1. Now, finally, let's do the derivative of y cubed, which is 3y squared dy over dx. And we need to differentiate the other side of the equation as well. However, the derivative of 0 just stays 0, right? All right, so what we now need to do with all of that is solve for dy over dx. Now, that was really easy in the first example, not so easy here. But I think what you're going to find as you do a few examples of this is that the solving part is almost always the same thing. So you'll get into a routine of doing it, and eventually you'll be able to do it with ease. Okay, I don't know if this y times negative 9 is bothering anybody. Just in case it is, we can write that as minus 9y, right? In case you don't like it in the other way. I wrote it like this to try to show you that this is exactly 1d2 plus 2d1, but really that should be a negative 9y. Okay, now what we need to do here is we have two terms that have a dy over dx in them, and so I want to pair those together and factor that dy dx out. And when I'm doing that, I might as well move the terms that don't have a dy dx in them to the other side because they're going to need to go over there anyway. Okay, so I just call this rearranging my terms. I want to keep the negative 9x dy over dx term, and I want to keep the plus 3y squared dy over dx term. I want the other terms to go to the other side. I can add the 9y over and subtract the 3x squared over to get them there. You could write it as negative 3x squared plus 9y. I just like to write it like that. Now that we have the two terms that have a common factor of dy over dx on this side alone, we can easily show that we could factor that dy dx out. Now, yes, you could also factor a 3 out of these two terms. If you want to do it at this step, go for it. If you don't, though, it's fine. It doesn't really matter. And you know what? I'm going to flip these around too. I'm just like, for whatever reason, feeling like we should write these pretty cleanly. And I'm going to write the 3y squared term first and then the minus 9x term. Are you okay with that? Am I allowed to flip those terms around? Instead of negative 9x plus 3y squared, I just turn them like that. Now that we have the dy over dx factored out, we can solve by dividing both sides by this quantity. So dy over dx is equal to 9y minus 3x squared over 3y squared minus 9x. We could factor a common factor of 3 out of these terms, and we could write it as, and cancel, right, divide it out. So we would have 3y minus x squared over y squared minus 3x in simplest form. That's not completely necessary. This would be just fine as a final answer. It's just scaled by 3. Or this is fine as a final answer. What's not fine is if you try to cancel other things. Don't do that. We don't have any other factors in the numerator and denominator to cancel. All right, how do you feel about that? I mean, a lot more steps than what you just saw here, but like I said, I think you're going to find as you practice these for yourself that it is the same steps throughout. So much so that you can very easily write out a set of steps for how to use implicit differentiation for most of the types of equations that you're going to see in calculus. So the steps are: differentiate both sides of the equation with respect to x. This WRT means with respect to x. And that means when you're differentiating a y, you multiply by dy over dx. Now, if we have equations of other variables, we'll talk about that. It's basically you're identifying what is the variable you were differentiating with respect to, and then if it is a different variable, you multiply by this derivative notation. Okay. Right now, most or all of our examples, I believe, are going to be in x and y form. Okay, step 2, you collect the terms with dy over dx on one side of the equation. That's where I was talking about rearranging the terms so that anything that does not have a dy over dx goes to one side and everything with a dy dx is on the other side. Step 3, you factor out the dy over dx if needed, if more than one term have it. And step 4, solve. Okay, this is a U-try problem, and it is pretty similar to the last example that we just did, so I am going to encourage you to pause the video right now and try it. I will do the same. I will pause it. I will put out my solution here, and then I'll come back and show you. And we're back. Here are my steps and my final answer to this U-try. I differentiated every term with respect to x. I moved terms that did not have a dy dx over to the right-hand side of the equation, and then I factored the dy dx out of the two terms that were left on the left, and I solved. Before we move on, I would like to show you the graph of this equation that we were working with. It's kind of cool looking, right? I love these asymptotes. We have a slant asymptote here, and we have a vertical asymptote going on. It's just lovely. All right, if you need more time with this example to check your work with mine, make sure to pause the video so that you can be sure that you have everything done for this U-try problem. I'm going to move on to our circle. Back to our circle. We're going full circle. Back to our circle. Find the slope of the tangent line to the circle x squared plus y squared equals 25 at the point -3, 4. So I'm going to sketch a little graph here. Maybe. -5, 5, -5, 5. Here's our circle. Ooh, and -3, 4 could be maybe about right there. It's about where I had my original tangent line to the circle in the warm-up. So I'm going to label that point. And we're going to calculate the slope of that line. So you should know that if you're doing the slope of a tangent line, that means differentiate. You know, nowhere in here does it say take a derivative or differentiate, but if you're asked to find the slope of a tangent line, you should know that that is what you need to do. So let's use implicit differentiation here. The derivative of x squared is 2x. The derivative of y squared is 2y dy over dx. And be really careful here. The derivative of 25 is 0. We've had a couple of examples where it was already equal to 0. This time it is not, but remember you are differentiating both sides of the equation. So if you have something here, you need to take its derivative, and if that's a constant, it goes to 0. Okay, we do not need to do our factoring step, but we do need to rearrange and solve. -2x divided by 2y can simplify to -x over y. And that is the equation of the slope of a tangent line to a circle that is centered at the origin. Now, let's find the slope at this particular point by subbing in -3 for x and 4 for y. It became a 3 because it's negative, right? -3. So the slope of this line is 3/4. Kind of makes sense, right? That looks like a line that could have a slope of 3/4. At least it's definitely an increasing line, right? And our slope is positive. So that's good news that we did it right. All right, example 4 is one where, again, we see the wording slope, so we should know that we have to differentiate. This time, however, we're not calculating a particular slope. We are finding where the slope of this curve is defined. So another way to think of that is finding any restrictions for your slope. And, you know, where it would be defined would be everywhere except for those restrictions. Okay, let's not jump too far ahead of ourselves, though. What we first need to do is differentiate. Implicitly, the derivative of 2y is 2 dy over dx. The derivative of x squared is 2x. The derivative of sine of y is cosine of y dy over dx. Now, we have two terms that have a dy over dx in them, and they are on opposite sides. So we need to bring them together. We could subtract this cosine of y dy over dx term to move it over to the left-hand side of the equation. And now we can factor that dy over dx out of those two terms that are together on the same side. Finally, solve for dy over dx by dividing by this quantity. Okay, now remember, what we are trying to do here is find where the slope is defined, Or remember, what we could think of that as is what are any restrictions that we have on this slope equation? And I probably should mention there are no restrictions up here, right? Nothing happened up there that would give us restrictions, because that would be an issue as well. And then we can say that, our slope is defined everywhere except for those restrictions. Okay, so where do we find our restrictions? Well, in the denominator, right? Whatever would make the denominator 0 would give us restrictions. So we want to think about, okay, 2 minus cosine of y cannot be 0. We don't want it to be 0, right? So that means that cosine of y cannot equal 2. Oops, cannot equal 2. And so what we should now think about are what are some values that we would be putting in here into the cosine that would give us 2. Okay, don't worry about the fact that it's a y, just what could go into cosine that, would come out as a 2. Nothing. This never happens. Think about the cosine wave. It oscillates between -1 and 1. Does it go up to 2? No. So is this going to happen? No. Is this going to happen? No. What does that mean? There are no restrictions. Yay! And if there's no restrictions here or here, then that means, therefore, the slope is defined for all points. Or I'll just say for the slope is defined everywhere. Good news. All right, let's move on to example 5. This one, I love thinking about it, but honestly, I'm just going to tell you now, when I start to talk about it, I sound dumb. I like thinking about the fact that what we're doing has this cool application, but when I don't know enough about it to really speak to it, to be honest. I teach math, and I know there's these applications out there. I love to highlight them when I can. I don't know enough of what I'm talking about, though. Take a look at example 5. In the law that describes how light changes as it enters a lens, the important angles are the angles the light makes with the line perpendicular to the surface of the lens at the point of entry. Profile lenses are often described by quadratic curves. When they are, we can use implicit differentiation to find the tangent and normal lines. That just sounds really cool in my mind, and I feel like I kind of know a little bit about that law. I never give myself the time to look up that stuff to know if I'm actually thinking of the right law. And even when I tried to just Google profile lenses to show some cool pictures, I don't even know enough about what it's saying to have a cool picture from all of the options on Google. I'm just I don't know. I'm in territory that I'm not confident in. So I'm just going to do the math and know that it has this cool application. Okay. All right, here we go. Find the equations of the tangent and normal lines to the ellipse x squared minus xy plus y squared equals 7 at the point -1, 2. Okay, so we can do that, right? If you want to pause the video and do that on your own and come back to me to, see if we're good here, go right ahead, because we know how to do that. We're going to use implicit differentiation. I'm going to do that over here. The derivative of x squared is 2x. The derivative of minus xy, that's minus x times y. Let's use product rule there. Is minus x times dy over dx plus y times -1, right? 2d1. Y times -1. Or, I just lost all that. This was 1d2 plus 2d1, but really it's minus y. Okay, is what I'm trying to say here. This is 1d2 plus 2d1. That minus is the derivative of -x, which is -1. plus not y squared anymore, right? We want the derivative of y squared, which is 2y, dy over dx. And the derivative of the other side of the equation is 0. All right, let's keep our terms that have dy over dx in them on the left. And let's move the other terms to the other side. So I'm going to add the y and subtract the 2x. I will then factor dy dx out. I'm going to write that as 2y minus x because I like to. Okay. 2y minus x. And solve to get our slope of the tangent line equation. Y minus 2x over 2y minus x. Do not cancel anything there. Do not cross stuff out. Nothing divides out. Okay. Now, that is the way we are going to get the slope of the tangent line. So now I'm going to move up here. And what I need to do is calculate the slope of the tangent line by taking this point, -1 in for x and 2 in for y. So that looks like this. 2 minus 2 times -1 over 2 times 2 plus 1. Because it would be, it's minus x and x is -1. So plus 1. And from that, we get what? 4/5. There's the slope of the tangent line. So now to write the equation of the tangent line, we can use point slope form, right? Point slope form is y minus y1 equals m times x minus x1, where this point can now be used for x1, y1, and our slope, our m, is 4/5. So it looks like this. Y minus 2 equals 4/5 times x, quantity x plus 1. There's our equation of the tangent line. I'm just going to leave it in point slope form. Finally, the equation of the normal line is the line that is perpendicular to the tangent line going through the same point. Again, I love to leave this in point slope form because it's going through the same point. So, I don't need to change my numbers here. I just need to take the opposite reciprocal slope. So I have y minus 2 equals -5/4 times the quantity x plus 1. And that is my equation of my normal line. Woo. Yay. I like it. I just like everything about this stuff. Okay. Finally, last example. Example 5, what we are going to do is a little practice with finding a second derivative implicitly. So let's, not get too far ahead of ourselves and start to worry about that, because that does sound kind of scary. Let's just start with what we know, and that is doing a first derivative implicitly. Okay, so I'm going to work on it here. You work on it for yourself, and then I'll talk about the next part. Okay. Derivative, derivative, derivative with respect to x, right? So we have a dy over dx for this term. Solving steps and simplified form. Now we're ready to do a second derivative. Okay, good news is that this is at least solved for dy over dx. So when we go to do our second derivative, take second derivative. we can just say that the derivative of dy over dx is the second derivative. On this side, however, we are going to need to use a quotient rule. Okay, so quotient rule, remember, is low d high minus high d low all over a low low, and away we go. Let's do it. Low is y, d high is 2x, minus high is x squared, d low is 1 dy over dx. All over a low low is y squared. Hey, I was just thinking about something that I feel like I should say because my brain's saying sometimes students ask about this, and sometimes, you know, I have students who ask about this way back in this example, and I forgot to mention it when we were doing product rule here. I'm not going to go all the way back and talk about it there. I'll talk about it right here, and it applies to the product rule examples as well. So when I was doing low d high minus high d low, I wrote my y and I didn't put a dy over dx beside it. And sometimes students say, well, why didn't you put a dy over dx there? You keep telling us to do dy over dx when you're doing a derivative. However, when I'm doing low d high, I'm not differentiating the y, right? I'm just writing it. And so if you were just writing a y term in your derivative rule, you do not multiply by dy over dx. It is when you are actually differentiating that piece that you multiply by dy over dx. Okay, I hope that makes sense, because again, sometimes I remember that I get that question. Okay, so we did it, by the way. There's your derivative. There's your second derivative. There's just one typical step that we do, you know, to clean it up a little bit, or to, I guess we could say, to make it better to work with. And that is right here. We don't leave this as a dy over dx. We don't leave it as a dy over dx because it could be written in terms of x and y. So that's one less variable that we would have in this side of our equation. Okay, what is it? I'm also going to write this, by the way, as 2xy. Are we okay with that? Can I do that? Question is, what goes here? What goes here? Something in terms of x and y go there. Do you know what it is? Well, right here, this says dy over dx is equal to x squared over y. So we change the dy over dx to what it is equal to in terms of x and y. Now, I usually tell my students you can leave it like that if you want to. It's messy, it's kind of ugly, it's not great to look at, but we've done a lot of work and I know you're tired. But however, I do want to give you like a cleaned up form. If you would multiply this here, get a common denominator, sort of simplify that complex fraction. And I'm not going to do all of that work just to save some time. I'm probably covered up. I know my picture is here, so let me erase that and move over a little bit. I am going to give you a simplified form, like I said, but I'm not going to go over the steps for it. Okay, again, this is fine as an answer, or when you do simplify, you should be able to get 2xy squared minus x to the fourth over y cubed. Okay, and it would be good to note that y cannot equal 0. Yay! All right, everybody. Thanks for joining me for this video. I hope it was helpful, and I'll see you again. Bye.